Hello everyone. So far we have seen, starting from the week 1, how to solve the diffusion equations, and then we also seen that what are the mechanisms of diffusion. We also understood the interdiffusion process and so on. So we have talked about different types of diffusion coefficients and so on. Now, in this week, what I want to focus, and that is one unique feature you will see in this particular course, is the techniques. How do we measure this diffusion coefficients experimentally? Okay, so because this d, the constant, or in the case of interdiffusion, it is not constant with composition, but how do we determine this d? What are the methods, experimental methods based on which we can determine d, is what is the content for this particular week. And today we will be starting with one of the most important techniques of measuring the diffusion coefficients, which is known as radiotracer diffusion. This is probably the most direct method to use it. So we will give a brief intro about various techniques to measure the diffusion coefficients. Then we will detail about the radiotracer diffusion and some points about what causes the deviations in the profiles that we get from the radiotracer techniques. So these are the keywords you can look for, and let us begin. So the techniques to measure the diffusion coefficient. So as I said, the question is, how do we measure the diffusion coefficients? Before actually we go to the techniques to measure diffusion coefficients, I will just briefly go through once again what are the different types of diffusion coefficients that we have encountered so far. So coming to the techniques, they can be divided into two methods. One is called as the direct methods, which are based on the fixed law and more phenomenological definition of D. Whereas there are also several indirect methods which are based on the phenomena which are influenced by the diffusion of atoms. So we will see examples of both these type of methods in this course, the direct methods and the indirect method. So as I said, so these direct methods and indirect methods, let me just give you some names here. These are listed here. So tracer diffusion plus depth profiling, then interdiffusion, resistance profiling, nuclear reaction analysis, NMR, these come under the direct methods. Indirect methods, you have mechanical spectroscopy, magnetic relaxation, nuclear magnetic relaxation, impedance spectroscopy, MBS, and QENS, quasi-elastic neutron scattering. So we will be covering some of the methods from the indirect methods, some of the techniques from the direct methods in the course of this week. Also, let me give you a brief idea about the range of diffusivities that can be measured using these techniques. So as you can see here, this the tracer diffusion. You can measure a very wide range of diffusivities, right from 10 power minus 23 to 10 power as high as 10 power minus 9 or minus 8. SIMS, for example, you see here, we will talk about this in the next lecture. You can measure more at lower diffusivities, you can measure more confidently, whereas EPMA or EMPA, sometimes they call it, is more suitable for the higher diffusion coefficients measurements. Similarly, in the case of indirect methods, you will see that ionic conductivity measurements gives you a wider range of diffusion coefficients, whereas in the case of MBS and QENS, it is towards more higher sides of diffusion coefficient that can be measured. So let us just briefly recall what are the various diffusion coefficients that we talk about. The most important are the tracer diffusion coefficients. So why this name trace? So in the diffusion studies, we quite often use the trace elements. Trace elements are labeled by their radioactivity or by their isotopic mass. and they are used in the very small quantities, almost in the ppm range, and they help us to measure the diffusion coefficients. See, if I want to measure diffusion, self diffusion of, let's say, element A, or let's say iron in iron, how will I know how much? If I deposit a layer of iron and allow it to diffuse, how will I distinguish which iron has diffused and which iron was already there? So therefore, what we use are the trace elements. That means instead of using a pure iron in the natural form, I deposit isotope of iron. Then when it diffuses, I can track using the suitable techniques. So this is what we refer by the trace elements, or the elements which are the isotopes. So isotopes, as you know, are chemically same, but they differ in the mass. So therefore, they do not give chemically any different information. There may be slight differences coming due to mass, but these are very minor, and we will see even how to quantify that later. So in the diffusion experiment, of course, you need a slight bit of concentration gradient, but it is so small that the overall composition of the sample practically does not change. My own experience, I have used this method, and I know, just to tell you, that the amount of tracer that we used to drop on the samples was somewhere in microliters, and that too is, the tracer is in the form of a solution. The actual amount is actually much below it. It is in the range of ppm. So it is really small quantity of the tracer used compared to your bulk. So therefore, you can say that the overall composition of the sample practically doesn't change. And from an atomistic viewpoint, it implies that a tracer atom does not influence the other tracer atoms, because they are so thin in concentration, they will not be interacting among each other. They will be just spreading out in the sample. So the analysis of this diffusion experiment, it gives rise to, or it yields a tracer diffusion coefficient, which is independent of the tracer concentration itself. So tracer are very important or appropriate to study the self diffusion of metric atom. They can also be used to study the diffusion of foreign atoms under dilute conditions. This technique can also be used to measure the diffusion along grain boundaries, and this is a very powerful technique we will see as we go along. Other than, so the tracer diffusion coefficients, as I said, that you can talk about self diffusion in pure metal. That means you can deposit a radioactive isotope of A on A. So this will give you the self diffusion, self tracer diffusion coefficients. Or you can deposit A star or B star on an alloy AB. So this is self diffusion in alloys. Or you can deposit a completely different element C star here, and it gives in the alloy A or in the alloy AB, and here you will get a impurity or a foreign diffusion coefficient. Then we also looked at what are interdiffusion coefficients, what are intrinsic diffusion coefficient, which are typically obtained from the diffusion couple experiments. So you can have a diffusion couple between pure element A and B, or you can have between the two alloys A and B of different compositions, or you can have between metal and hydrogen also, and you can measure the interdiffusion and intrinsic diffusion coefficients. Remember that interdiffusion coefficient is a measure of, in a binary system, if we talk about, it is a measure of intermixing. Therefore, there is only one interdiffusion coefficient. There is no separate interdiffusion coefficients for A and B, whereas the intrinsic, it is defined for A separately and B separately. But intrinsic diffusion coefficients differ from the tracer diffusion coefficients in the respect that they are the coefficients determined when there is a driving force present. So what we do in the tracer diffusion experiments? Let me just show you the schematic. So what you do is basically you take a sample, typically a disc-shaped sample, on which you deposit the tracer. Tracer is normally a radioactive isotope, as I told in the previous slide. If you are using an alloy, it can be an isotope of one of the constituent elements, or it can be not a constituent element. Then you are measuring a impurity or a foreign atom diffusion. Then you take this sample, and the way we deposit this tracer is usually in the form of a dilute solution. So let's say if you have a radioactive isotope of cobalt, then that is diluted, that is mixed in a HCl or some suitable acidic solution, and that solution is deposited on the sample, allowed to dry, and then you do the diffusion annealing. And this annealing, before doing the annealing, actually you put the sample, you seal the sample in an argon atmosphere in a quartz tube, and then you diffuse, allow the diffusion to occur during the annealing. And as a result of annealing, the tracer will spread into your sample. After this, then what you do is you reduce the diameter of the sample. Why we do it, I'll shortly come to it. And then you do what is known as serial sectioning. So as the name suggests, sectioning means you section these samples into very thin slices, so that you can count the radioactive material, and then based on that you generate the profile, which is depending on the conditions, it can look like this, with one profile, with two slopes, and so on. So due to the high sensitivity of nuclear counting facilities, these radiotracer studies are often superior to other techniques. See, the key here is, ultimately in any diffusion experiment, what you want to measure is the concentration versus depth, so that the slope of it in some way can give you the diffusion coefficient. So to measure the concentration, you need a certain amount of the tracer or certain amount of element to be present to be detected by the characterization technique. So if you use your microscopic characterization, the limit, the very lower limit or very low concentration you cannot measure. Whereas in the tracer, because you are measuring the radioactive counts, you can detect even the ppm of the amount of the tracer present. Therefore, these are very sensitive techniques, and therefore you saw in the first table that I showed, that in the tracer diffusion technique you can cover a long range of diffusivity. You can measure very, very low diffusion coefficients using the tracer techniques because of the sensitivity of the nuclear counting facilities. And here you can study the self-diffusion coefficient in a very straightforward manner, and using the radioisotopes of the matrix atoms. And as I indicated before, the typical tracer concentrations are less or even much less than ppm if the activity of the radioisotopes are high. So basically what it means is that since the tracer concentrations are less, you are measuring diffusion coefficient in a chemically homogeneous solid. So your tracer is not influencing the composition of your sample. The complications due to chemical gradient. So because there is no concentration or chemical gradient, it doesn't play a role here. And the thermodynamic factor, what we saw in the previous lectures, is unity. And you can use evaporation, dripping of a liquid solution, or the electrodeposition of the radiotracer onto the surface to deposit the sample. So at the deposition step, you can use evaporation. You can, as I said, you can directly drop using a pipette to the surface, and or you can use a electrodeposition also. Then when you do the diffusion annealing, you want to ensure that the temperature is controlled to precise values, so that you get a interpretable data. And you also need to take care that annealing is done in argon atmosphere, so that no oxidation or any unwanted reactions happen during the annealing process. So, after the step of diffusion annealing, the first actually step that we do is the reduction. So, reduction in diameter of the sample is done like this. So, this is your sample which is placed on the holder like this. This is typically a copper holder, and this is the grinding paper, this grey color, which is pasted on a grinding wheel, and this assembly is rotated as well. This is also rotated. So, so you see here, this is rotating and this is rotating. So, that will generate the grinding friction, and the sample is reduced in the diameter. Why we need to reduce the sample in diameter is because when you are depositing the tracer, ideally for the analysis you want the tracer only to diffuse in the depth direction. So, that is where you can use the Gaussian solutions that we derived earlier. But what can happen is that some of the tracer can diffuse through the surface also. So, the tracer can diffuse to the surface and reach here. That will give erroneous values if measured along with your tracer diffusion that is happening in the depth direction. So, therefore, what we do is we reduce the diameter of the sample so that those lateral diffusion effects can be ignored or it can be removed. Then comes a very important step of the serial sectioning. See, here we are talking about the diffusion depths which are very, very small. So, you cannot use your conventional, let us say, wire cut or so, because that will provide very thick sections, and this will not lead to a generation of a statistically reliable data. Although that kind of a very fine cutting is used in some alloys which are very, very soft, but most of the cases what you do is you perform what is known as mechanical sectioning. So, mechanical sectioning, what the schematic is looks like this. So, what you do is you have a grinding plate here on which you put a grinding foil. The foil looks something like this. This is a mylar foil, and on this foil is your sample inverted and it is attached to the sample holder. And this grinding plate, the bottom there is a small suction that is created so that your foil sticks to the grinding plate. So, it is perforated, actually the grinding plate is perforated so that suction is created and the foil sticks to that, and then the sample is inverted onto this foil using a sample holder. Now, this is rotated, this grinding plate is also rotated. You can vary the time of the rotation, you can vary the speed of the rotation, you can also place extra weights here, so that the amount of the material that is grinded is can be changed. Why it is important is because when you are near the surface, you want to make very thin sections, so that you can use the lesser speed, lesser revolutions and all. So, in the beginning you can take out very thin sections. As you go more and more deeper into your sample, you may want to make thicker sections, and that is where you can reduce or you can increase the rotation speed, or you can put more weights on the sample. So, after the grinding is done, you can see the here the residue is collected like this, the section layer is collected like this, and this grinding foil is then folded and it is put into the appropriate vial, which is then taken to be measured in the detector. Remember here how we know that how much thickness of the layer we have removed. So, to do that, what usually do is, along with this sectioning setup, the nearby there is a balance, weighing balance. So, before each section you take the weight of the sample, and after each section you take the weight of the sample. So, the difference tells you that how much weight has been reduced, and since you know the density of the sample and the cross sectional area of the sample, you can estimate what is the thickness that is removed. And therefore, it is very important that while sectioning the sample is very parallel to the grinding plate. This is actually done. This is the very first step that they teach you when you do this kind of experiments, what is known as calibration. So the sample should be parallel, and that is once that is ensured, then you can safely assume that based on the weight, what is the thickness that is removed. So then you take this foil and you put it in the detectors. There are two types of detectors. So there is something called a LSC detector, which is liquid scintillation counter, which is for the beta isotopes. And if the isotope is a gamma isotope, then what you use is a germanium detector. So this is one example of germanium detector. So if you are putting liquid scintillation counter, as the name suggests, there is a liquid involved. So what you do is you put your foil in this vial and you fill it with the liquid. And this liquid is typically an organic liquid, a benzene derivative. And this vial goes inside this detector. Whereas if it is a gamma detector, there is no liquid involved. You just put your file inside this kind of a tube, and then you put a cap here so that nothing comes out, and this goes into the detector here, and then the counts are measured. So there are certain isotopes which are beta isotopes. There are certain isotopes, gamma isotopes. For example, nickel is nickel 63 is a beta isotope, whereas cobalt, manganese, zinc, these are all the gamma isotopes. So then, just to tell you, these images were taken at the radioisotope lab at the University of Münster in Germany, which is the only place where this kind of diffusion measurements are currently being conducted. So as I mentioned, there are two types of detector. One is the LSC detector. In the LSC detector, what happens is the radioactive molecules, which are the beta isotopes. So beta means the electrons. So these electrons interact with the solvent molecule and make them in the excited state. So this solvent is nothing but the liquid that I mentioned, and which generates what is known as a fluorescent molecule. And this fluorescent molecule is then captured in a photomultiplier tube, and the signal is amplified. You also have another type of detector, which is a semiconductor detector, which is used for the gamma isotopes. So when the gamma radiations that are emitted from the isotope, they impinge on the semiconductor. So this is one example, cadmium, zinc, tellurium, and that generates a pair of holes and electrons, which is then conducted in a circuit where the voltage is measured. And the more the counts or the more the radiations, the higher is the voltage signal, and that voltage signal is used to detect the radioactive counts and so on. So now how do you do the profile analysis? So basically what you are measuring is the radioactive counts, and you assume that these radioactive counts are proportional to the concentration of the tracer. So basically you assume that the concentration is proportional to the radioactive counts, which is not an unreasonable assumption. So more the amount of tracer you put, you will tend to get more counts. So therefore, what you do is that you then take that as a concentration, the radioactive counts you take proportional to the concentration, and we know that the concentration will be described by a Gaussian function, which is something like this. C is equal to m by root pi dt exponential minus x square by 4 dt. This as you will recollect, this we had done in the lectures of solution to diffusion equation. So here this is a thin film geometry case where only the layer is present at the surface. So this is m by root pi dt exponential minus x square by 4 dt. So here, as I said, that in order to ensure that you get a good fit, you have to see that the parallelness of the sections to the iso concentration contours. And for the radioactive tracers, the specific activity per section is proportional to the tracer concentration. Specific activity means the activity per unit weight of the section. So, as I said, specific activity is obtained from the section mass and the count rate. So, for the short-lived radioisotopes, the half-life corrections are also necessary. Remember that if let's say there are some isotopes, for example, let me tell you chromium isotope. So, chromium isotope has a half-life of 27 days. Now, if your annealing experiments or the sectioning experiments go for a longer time, there may be an automatic reduction in the activity of chromium, or so to say the radioactive counts, due to the natural decay. Okay, there is also a decay happening due to the diffusion, but that we want to separate out. So, therefore, for the short-lived isotopes, half-life corrections are also necessary. So, if you have a thin layer sectioning experiments, basically how much do you want, because I told you that you section different layers, how many layers I should section. So, typically you see that the drop in concentration is about 3 orders of magnitude. Till that point you section. For self-diffusion measurements or in the metallic alloys, typically 20 sections, 25 sections are generally sufficient. But that is also dependent on if you have chosen the temperature and the time correctly. For example, just sharing my own experience, the very first experiments when I did, I chose a temperature which proved to be very high for that particular system, and I ended up sectioning some 100 sections, because we want to see that ultimately you reach a drop of 3 orders or more in the concentration. So, I had to section a lot. So, but typically if you have chosen the time and temperature correctly, about 20 to 30 sections should be sufficient. So, this is how the typical tracer penetration profile look like. You plot log of specific activity versus x square. So, you get these points, and then you fit the line and the slope of this as is evident from the previous this, that if you plot log c versus x square, the slope of this is 1 by 4 dt, which gives you the diffusion coefficient. Sometimes typically when you want to measure the very low diffusion coefficients, you see for example, you may notice here the diffusion depths here are about 30 or 300 microns actually, and therefore these are very large diffusion depths. But sometimes what can happen is that when you are measuring diffusion coefficients at lower temperatures, the diffusion depths may not be high enough. So, diffusion depths may be very small, let us say even in the range of nanometers. In such a case, if you use a sectioning, then you cannot section nanometers using the mechanical sectioning, because it rotates even at the smallest speeds, it will definitely take out the section in submicron regimes at least. So, therefore, for measuring the low diffusion coefficients, what you use is something called as ion beam sputtering, which where your sample is placed here. This is your sample on the sample holder, and you impinge an ion source on your sample, and which results in the sputtering of the material of the layer. So, you measure the sputtered layers. So, you can control the voltage and the current. So, you can control how much thickness of the material you want to be removed. But here you can remove the sputtering thicknesses, or the sputtering layer thicknesses can be in the range of nanometers. So, you can collect several such layers, 20, 30, 40, and then you can measure the radioactive counts. So, after ion beam sputtering, if you do a typical penetration profile looks like this. The nature of the profile is similar to what you saw in the mechanical sectioning, but have a look at the depth here. So, this is 6 microns. So, within 6 microns you are able to have so many sections. Okay. So you can do this only with the ion beam sputtering, because each section can be in the order of few nanometers. So that is possible using ion beam sputtering, not with the mechanical sectioning. So if everything is fine, then you get a nice Gaussian profile. You get a very nice linear fit like this. The slope you measure, it gives you a diffusion coefficient, and it is all fine. But always you get certain complications in the real systems. So what are the possible deviations that can occur in these Gaussian profiles? The first is the grain boundary diffusion. So if there is a grain boundary diffusion occurring, then there can be, that means that along with the lattice diffusion, there is also a grain boundary diffusion occurring. So you end up getting two branches in the profile. So you will not see only one single branch like you saw here or in the previous case, but you will see two branches, and then they have to be fitted with an additional function which looks something like this, a6 to the power 5. So we will see more about this later, but this then the Gaussian function has to be modified to take into account the profile that is or the branch that is generated through the grain boundary diffusion. Let me just see if I can also schematically draw, or actually this was present in one of the schematics that we showed before. So here actually this schematic, what you see here, this is actually with the grain boundary diffusion. So this tail actually corresponds to the grain boundary diffusion, whereas this is the lattice diffusion. So when you have grain boundary diffusion, the profile is no longer having one single branch, but it may have multiple branches. So then that is the first reason for deviation in the Gaussian profile. And then the next one that we come to is the evaporation loss of the matrix atoms. So what can happen is when you are annealing, if your sample has a high vapor pressure, then it can get evaporated during the diffusion experiments. So you may have this case with zinc or tin and so on. So if the removal is continuous at a rate v, then the solution is modified something like this. So m by 1 by root pi dt exponential minus eta square minus v by 2d error function of eta. You don't have to memorize this, but the intention is that you appreciate that the deviations can cause the change in the mathematical equations, and it can cause change in the profile that is obtained from a standard experiments. Also, it is possible that tracer itself may be evaporated during the experiment, and again if the tracer has a higher vapor pressure, then it can deposit, it can evaporate from the surface very fast, and then the thin film solution is no longer valid. And if you have an outward flux which is given something like Kc0, where K is the rate constant for evaporation, then the solution can become extremely complicated. So again, as I said, that you don't have to memorize this equation, but you have to appreciate that the deviations can be there because of the evaporation loss. So these are the three important deviations that can occur in the Gaussian profile during the tracer diffusion experiments. Then one more question that may come to you is, probably you know that for each element there are different types of isotopes. There is not just one, there are several isotopes of an element that can exist. So which one I should use for the radiotracer experiment? Will there be any difference if I use different isotopes? So for example, for element A, if I am measuring, should I use A star or some other isotope A double star? Similarly for the other cases as well. So as I said, the question is that, do you think that different isotopes will diffuse at different rates? The answer is yes, the different isotopes will diffuse at different rates, and the answer lies in the one of the factor that we saw when we were discussing the atomic mechanisms, which is this frequency. So this frequency which comes in the D0, if you remember the expression, in the D0 we have an expression for the D0 has a component of nu naught, and this nu naught, which is the atomic vibration frequency, is inversely proportional to the mass. So a heavier isotope will move with a lesser frequency, a lighter isotope will move with a higher frequency. So in principle, the D0s will be different if other things are same for different isotopes. So people actually have tried to measure how much is the isotope variation influences the diffusion rate, and some of the combination of isotopes which people have used are mentioned here for the carbon, sodium, iron, cobalt, zinc, copper, silver, and gold. However, for many of the alloy systems, the isotope effects are not that significant, and if I use a 55 iron or a 59 iron to measure the diffusivity in steels, practically they may be very similar. So therefore, the isotopes do have a different diffusion rates, but for most of the metallic alloys, those rates are not, those differences are not very significant. So then just summarizing some of the advantages and the limitations of this technique. So the advantage is that it has a higher sensitivity of nuclear counting facilities. So you have reliable diffusion coefficients typically when you have the lower diffusion coefficient range. Then this measures the most basic diffusion process in the straightforward manner. And since the concentrations are less, you can use very less concentrations if you use radioisotopes of higher specific activity. And because you use the lower concentrations, you can measure the diffusion coefficients in a chemically homogeneous solid, and no complications of chemical gradients come into picture. And as we have indicated, that large range of diffusivities can be measured in a wide variety of materials. What are the limitations? There are some very important limitations also. The first is the availability of the suitable isotopes itself. For all elements, the isotopes themselves may not be available. For example, aluminum, it is not possible to get a suitable isotope. So usually when people want to measure the diffusivity of aluminum, they don't use the aluminum isotope, but they use a gallium or a zinc isotope which mimics the diffusion of aluminum. So availability of suitable isotopes is an important limitation. For example, scandium, if you want to measure the diffusivity, people measure the diffusivity of scandium, but scandium half-life is, if I remember correctly, is in few hours. Or zirconium also, for example, they are very, very short-lived isotopes. So then you have to complete everything within only a specified duration, and you have to take care of the half-life corrections and so on if you want to measure any reliable diffusivities. The setup that is required has a lot of safety requirements. This is the most important limitation. That's why, in fact, you have only very few places, one dedicated lab. The only place is the University of Münster, from where I showed you some figures, where such diffusion measurements are done at a larger scale. There are few atomic research centers where this might be, the radioactive isotopes may be handled, but dedicatedly diffusion measurements are done currently only at one place. This is because there are a lot of safety requirements that are needed. A lot of safety regulations that need to be followed, and there is therefore that is not very easy. In fact, the disposal of waste of radioactive isotopes, you can imagine that if your sample is contaminated with a radioactive material, then you can no longer throw it into your normal dustbins. There is a protocol for disposing of the radioactive waste. Okay, and that plus a lot of safety concerns of the users. In fact, when we used to work in such a lab, every 6 months you have to undergo a medical checkup to ensure there is no radioactive contaminations in your blood. In fact, why every 6 months? Even every day when you go to the lab and you come out, you stand on a detector every time you have worked on in the lab to make sure that there is no spillage unknowingly happened on your body, so your body is not giving radioactive signals and so on. So a lot of safety requirement is to be there for this particular setup. And another is that post diffusion annealing, post diffusion characterization is not possible. So that means if the diffusion has happened, and now if I want to measure that, or I want to characterize where the diffusant has gone, whether it has gone to the grain boundaries or it has gone to the lattice, any post diffusion characterization is not possible. So whatever the characterization you have to do, you have to do it before, but after the diffusion annealing, you cannot do the characterization. So these are some of the limitations of this technique. So thank you very much. If you have questions, you can post it on the forum, and we will continue with some other techniques in the next lecture. Thank you.